All right, so welcome. Here we go. This is the third day or the beginning of the second week of our kind of subsection on software engineering. Good to have you guys back. We were just talking about our weekends. Had a fun weekend. Anybody do anything particularly exciting this weekend? Fun. I was saying earlier, my wife, what she wanted to do for Mother's Day was to keep everybody happy. And we've got 4 teenagers in the family, so we went to see the Avengers Civil War, the new Captain America movie, and that was the fun thing that everybody was excited about. So that was our fun thing yesterday.
So the question is, did mom go with you or did mom stay back?
That's a great question. She went along.
Okay.
She's pretty fun loving. Yeah. that could have been a possibility is, honey, why don't you take the kids? Be home. No, that was fun. That was fun. All right. So what I'd like to do today, I've got an agenda here, and I want to just take a couple of minutes. We won't spend long on it. Just review the quiz that I put out there, and several of you took that. And then I want to walk through just a couple of things. Only a couple people turned in some software requirements artifacts. Just briefly look at functional and non-functional requirements and evaluate those a little bit. And then most of our time today is going to be spent on UML. I want to walk through different kinds of diagrams, and we'll create some diagrams. I've started some in a tool, and we can interactively add to the diagrams that I've created. And feel free to stop me, ask questions on all of that. And we'll be reviewing the things that I've started and adding to them. And then if we've got time, I'd like to talk a little bit about design patterns. And I'll just put kind of a teaser out here for that real quick. Design patterns, the idea is if there are great designers out there, and we're talking about software design here, but this can be true in many different areas. In fact, the concept of design patterns was stolen or borrowed from architecture, where this guy Christopher Alexander, a very well-known architect in terms of building traditional architecture, he said, how can we teach young architects the things that really experienced, really seasoned architects know, expert architects, how can we pass that on to them? And he started to capture designs, patterns of design, ways that he solved solutions, and ways that he saw many people solving the same kinds of problems, the solutions they would come up with, capturing them, giving them names, and talking about what the context was, so that they could then document them in a book and a catalog and pass them on to younger architects. And so we do the same thing in software design. There's a whole collection of these different design patterns. And so I thought I'd give just a few examples of some of those design patterns. And you might hear software designers, software developers talk about some of these terms, things like facades and template method and adapters and iterators. And those are some common things, or singletons. And so those are things that they should all understand, and maybe it might be useful to know what their vocabulary is. So that's a little bit of what design patterns is about. So we'll look at a couple examples of that. Any questions before I jump into our agenda then?
I'd love to get some feedback when we do the UML of anybody who submitted theirs. I know I kind of struggled with it a little bit and tried to lay out a few base things, but especially the connection part and understanding those would be great.
Okay, you bet. Sounds good. I don't want to, point anything out, but you might be the only one who turned anything in. There were not many submissions, but it's still open, and so I'd love for everybody to take a stab at it and create some diagrams. So hopefully that'll be more clear after we go through it today. Okay, so I want to just quickly go through the quiz out here, and most people who took it did quite well, which is great. I'm glad to see that. There were just a couple of questions that a couple people missed, and so real quick, this first one, which statement most accurately describes the iron triangle with the traditional waterfall software development lifecycle? And so the answer is with traditional, typically what we do is we fix the requirements and then we estimate the resources and the date that, you know, how long is this going to take? How much money is it going to take? Whereas when we flip that with Agile, typically we will fix the resources and the date. So we'll say we're going to do sprints. They're going to be 2 weeks long. This is how many people are going to be on them. So we know how much it's going to cost for the next 2 weeks and when it's going to be done. And then we estimate how many requirements we can get done in that time frame. That's the idea. I just today had somebody ask me, hey, can you give me an estimate on some consulting work for this summer? Well, it's really hard. You know, they gave me just brief little information, high level, kind of abstract. How do I estimate that accurately? What are my options? Well, one option I have is I can give them a really high level estimate and say maybe it's plus or minus 1,000%. You know, oh, I think that'll take me about 4 weeks to do, you know, maybe 160 hours, plus or minus 1,000%. If I know more detail, then I can, you know, make that more accurate of an estimate, but it's going to take me time to get more detail. So I'm going to have to spend effort. So, you know, that's some of the balance. And so I suggested, hey, let's do this in an agile way. How about if, you know, I'll spend 20 hours a week for 1 week, and you know, I'll do everything I can as fast as I can. And at the end of that week, you reassess and say, did I get, you know, you can adjust what you want me to work on, and you know, I'll fix the amount of time. I won't go over this budget and when it will be due, and then we'll let fluctuate what I actually work on according to you. And he's still thinking about it. We'll see what he does, but it's kind of taking an agile approach is the idea. Yeah. And sometimes that's a good way just at the beginning to help you learn enough in order to make a better estimate. Even if they require an estimate, you can do that to get enough information. Okay, so that was kind of a tangent there on the first question. Second question, which is not one of the 3 questions typically asked in a daily Scrum stand-up meeting. And of course it was C. Whose turn was it to bring the donuts? I remember on a final exam, I asked something like that in one of my classes, and the 3 questions, I asked, what are the 3 questions? And one of the students had no clue. They didn't remember. They said something like, who forgot to bring the donuts? Whose turn was it to bring the donuts? Why didn't you bring more donuts? Typical student answer when you don't know. Number 3, what's the typical length of a Scrum sprint? It's usually in terms of weeks, and so 2 weeks is pretty common, sometimes up to 4 weeks, but not usually more than that. What kind of a prototype implements a thin slice of functionality? This is one that several people got wrong. And so the idea, we talked about a horizontal prototype being looking at all of the screens, so all of the user-facing stuff. And that's a horizontal prototype, whereas a vertical prototype is just taking one little thin slice of functionality and taking it all the way from the user interface down through every technical aspect of the system, you know, going through touching all the network connections, the database, whatever other systems we want. And so that was the concept of a vertical prototype. And then 5, what kind of requirement details a user goal with everything from a description of the goal and actions to preconditions, postconditions, and normal and alternate flows. So this is the most detailed of them. This was a fully dressed use case. You see there. And then the last one, what kind of tool facilitates sharing and merging of software code amongst collaborative developers? And that was a software configuration management. Git is an example. Also Bitbucket and Subversion are some examples. Mercurial is another one. Okay. Any comments, questions on the quiz? Okay. Let's look at a couple of functional requirements then that were put out there, and let's just, you know, analyze them, give some feedback on them real quick. So both of these functional requirements are in the form that we suggested of a functional requirement. The system shall. Okay, what shall the system do? The system shall display the current fuel consumption and estimated range based on a current average fuel consumption. Okay. So what do you like, and maybe what could be improved on that functional requirement? Is there anything that's ambiguous there? Anything that's not clear?
maybe like within how accurate the estimate needs to be based on some sort of, like plus or minus some sort of tolerance on that.
Okay. Okay. So that could be under functional requirements, but it might be more likely under non-functional requirements. How accurate would it be, perhaps?
Yeah, that's true.
Yeah, but that's a good point. Is there any word in there? I see one word that maybe raises I mean, I think this is a good functional requirement, but there's one word there that maybe raises a little bit of a question in my mind is, how is that defined?
Maybe current, based on, is it the current trip or like the entire history of using the car?
Yeah.
I'm assuming it's a car, but maybe it's not a car.
Right. Yeah. We assume there's some context here that we're not given, and so we have to kind of make that up here. But yeah, that word current is the one that I would focus on and say, okay, can we be more specific there? What does that mean, current fuel consumption? Is it really at a moment in time, like within the last second, or within the last minute, within the last hour? What does that current mean? How is that calculated? Okay. Well, I don't want to spend a lot of time on them, but those are the kinds of things you might look at as you're thinking about them. Let's look at the second one real quick. The system shall display the total price of all items currently in the user's cart, including tax. Is it clear? Is it testable? Is one of the, how would we know when that's done? Could you imagine creating some sort of a acceptance test saying, give it these inputs and this should be the output?
Would it, or I guess what might be ambiguous is the shipping, because isn't it tax local?
Okay. Yeah, tax is usually localized, sales tax perhaps. We would assume that.
Okay.
But test cases would take care of that.
Okay.
Well, for this test case in San Luis Obispo, California, this is the tax rate, and so this is what the tax should be in this particular test. And then we'll do another test in, Dallas, Texas, and this is what their tax rate is, and this is how it should be different. And so that would all fit within this functional requirement. So, yeah, I think it's a pretty good functional requirement. Okay, so two good examples there. And let's look at two non-functional requirements. And so the first one, the system should accurately estimate the range to plus or minus 10% of the displayed value. Again, we're missing some context. What exactly is the range here? I don't know. But what kind of a requirement is it? It's non-functional. Is it looking at accuracy, reliability, it's security? It's talking about accuracy. Is it clear? Should estimate the range plus or minus of the displayed value. Yeah, I feel like we need some more context to know what's the range, and how's that computed. Okay, and then the last one, the system shall display a notification announcing the name and price of an item within 3 seconds of when an item is placed in the cart. Okay, so it gives us an idea of how it should do it and how quickly it should do it. So speed, performance, which is good. We assume there's probably some functional requirement that says that the system shall display a notification and might tell us what a notification is. That's not what we're trying to accomplish here in non-functional. We're just talking about the part of how fast it does that. So those are good. Remember, as we talked about, especially on user stories, which we'll look at these two in a second, this acronym INVEST, and especially with user stories, but we can also use this on functional and even non-functional requirements that are each of these things independent. They can be done separate from the other use cases. Are they negotiable? meaning that we can negotiate what is the scope of this, and how long is it going to take. Estimable is what that gets to. And negotiable sometimes means that we can break it up if it's too big into smaller things, and that ties into small. It must fit into an iteration. Is it valuable to the user? Is it testable? How do we know if it's done? And so that's our guideline. So let's use that real quick on this one. So as a vehicle user, I can reset the continuous average value of the fuel consumption to account for each new tank of fuel. Okay, so it fits the form, which is great. As some kind of a user, I can do something. The question is, so that, okay. So that here, so what I can do is reset the continuous average value of the fuel consumption, and then to account for each new tank of fuel. So that's partly what we're doing. Probably what's missing here is the reason. What's the value in doing this? Why do this?
Don't run out on the side of the road or on the freeway.
Yep. Yep. Yeah. Is it independent? Okay, so what if this is too big? I can reset the continuous average value of the fuel consumption. Is that something that we can do? Actually, the second one maybe is a better example of that. Can we break this one up? As a shopper, I can look up other customers' reviews of items so that I can decide if I want to keep an item in my cart for purchase. Okay. So is there anything that's not clear here? Definitely has all three pieces of the format. Oops, sorry about that. I would say, so just to wrap this up real quick, I would say that I can look up other customers' reviews of items. Well, what kind of trouble could I get in with saying that I can look up other customers' reviews of items, and how big is that? You know, it's possible that that could be really large. What if there's 1,000 reviews of items? And so do I need to be able to see all 1,000 reviews and be able to, you know, page through them? Do I need to be able to search those customer reviews? And what does that mean, look up other customers' reviews? Is that searching that's implied in there? And so I'd maybe refine that a little bit. And especially if I would, you know, as I talk about that, maybe I decide, oh, that's a little too big. I need to make it smaller. How can I make that smaller to make sure it fits into this 2-week iteration? Anybody have a suggestion of how to word that middle part there to make it a little smaller? All right, Kurt warned me that I have to start calling on people. I'll put something out there. So I can look up other customers' reviews of items. So maybe I can view, rather than look up, simply to see that I can view the 5 most recent customers' reviews of items. That might be a way of making it simpler and narrowing the scope a little bit. That's something I think, oh yeah, definitely, I know what the screen might look like and what kind of controls I need in order to be able to be able to view 5 most recent customer reviews, rather than this broader looking up and not knowing how many, not having any limits on them. Okay, so those are things that we do, and those are things that you guys might do as you're working with software engineers, is refining those and going back and forth on to make their life manageable so that they deliver to you software that you're happy with. But focusing on the details of those things is useful. Okay, so let's jump into, unless anybody wants to stop me, let's jump into the UML stuff. Okay. So I thought I would start just mentioning a couple of slides here of before we did things in an object-oriented way. We did things in a procedural way. The idea of procedural programming, procedural design looks something like this. Let's say that you were given a task to create a software system that allows two users to play tic-tac-toe against each other at the same computer. Okay? What might that look like in terms of a procedural design? Probably what we used to do is something like this. We create a hierarchy or a module chart. We would often do a top-down design. So we would start with what's the big thing we're trying to do and then break it up into modules. What are the pieces of that? And so playing tic-tac-toe is the big thing we're trying to do. What is involved in that? Well, we need to create the board, the tic-tac-toe board. We need to be able to play the game, and then at the end we'll display the winner or whether it was a tie. And then a part of playing the game is these things, you know, getting the player's next move, verifying the move, checking for a winner, displaying the board. And you can just keep breaking those things down until you get to the point where the software developer says, oh yeah, okay, that's easy to do. That's, you know, that's a function, that's 10 lines of code, I can do that. So it's just kind of this top-down design. That was a traditional design, and we still use that in some ways, but we've changed our way of thinking now to be in terms of objects. Now, the other thing we would do at that time is we think of what's the data, what are the different data structures? So how do we structure the data? Well, here, to a tic-tac-toe board, the reason I chose that is it's a nice visual thing we all are familiar with, and you can represent that pretty easily in what we would call a two-dimensional array. So an array of one dimension might just have, you know, a three-element array might be this first row here. That's an array. An array is a grouping of elements that are all the same type. So here they might all be a single character. Either it's an X, or it's blank, or it's an O, are the three options. And so you can represent that by a character. And so we have three of those in a row, and so that's an array of three of them. But here we want a two-dimensional array. It's a 3x3 grid. So that's our data structure. And so we might think of what are the right data structures as well as the hierarchy module chart. And then the next thing we might do for each of the element in there is write the algorithms that we're going to have. And so like here might be the algorithm for playing the game. While we do this, and there's another while loop inside of there, and then some steps, and then an if, then else, and another if, then else. And so we might write that, and then we can directly translate that into code. That might be what our design looks like in procedural terms. But in object-oriented terms, instead, we do things where we identify what are the different things, the objects, and how do they interact with each other. And that's what we're going to do in UML. Let me just jump over there real quick to a tool. And so we're going to use this. Here I'm using Violet, which is one of the two tools that I suggested you might use. And I can, yeah, and this is a class diagram, just a high-level class diagram that has some different objects in it, or classes, I should say. And often we'll start with just identifying what are the nouns in our requirements. What are the things that we need? And sometimes these correspond to real-world things. Sometimes they're concepts, but they're things. And so I've identified what some of those are and what some of the relationships are between them. Then we can go start adding detail to them. And I'm going to come back to this here in just a little bit, and we'll add to this diagram in a little bit. But that's usually where we start in object-oriented design, rather than, you know, breaking things down. And so we identify what are the different items or things, or we'll call them classes. Okay. So in UML, that leads us to how do we design things graphically in UML. We don't want to just write software. That's too much work. And so we want to use graphical notations. And so what is UML? It stands for Unified Modeling Language. And just a little bit of history on there. So I mentioned here the three amigos. So back in the 80s, when object-oriented programming was first becoming popular, and definitely in the 90s this was the case, there were a variety of different ways of drawing and designing object-oriented systems. And the squares that we use now and the different lines and the different kinds of arrowheads on the lines, they mean a certain thing. Okay, it's a language, it's a visual language, and they mean a certain thing. But back in the 80s and 90s, there were different modeling languages, and they were competing. And there was a company at the time called Rational Software, and they had this great idea that, hey, we build tools, and we don't like having to build tools that support different modeling language. We really wish that we had one unified modeling language that everybody used. And so they did a smart thing. They took the three guys who had the leading, most popular modeling languages, and they hired them all, gave them big salaries. They said, you're going to come work for us, and you're going to sit in a room for 6 months or however long it takes in order to merge your modeling languages into a single unified one. And then you're going to come out, and we're going to declare to the world that the modeling wars are over and we've won. And they did that. And it's a very kind of an audacious thing, arrogant thing for them to do. But fortunately, they did something very smart with it. And they said, here, this is the new unified modeling language. This is what everybody's going to use. But we recognize we're a company and we can't control what the world's going to use because another company is going to compete with us. So instead, we're going to release this to a standards organization. An organization is called OMG, and I always get a lot of grief for that. OMG, it stands for Object Modeling Group. Okay, and now texting has totally changed that. And so they're this third-party, independent standards organization, and they control the UML. And that was really a smart move on their part to say now the company is not in control of it. So that's a little bit of the history of how it came about and why we call it the unified modeling language, because it took these good ideas from the different leading modeling languages and put it together. A little bit about how you use the UML. I see software engineers, software developers using UML most often probably as just a sketching tool, whether you're just at a whiteboard and drawing pictures or just doing it on paper, and then you throw them away. You just use it in order to think about the ideas and how are we going to design it, and then you go start coding it. And that's a very common thing to do. However, there are some organizations that, and this was very popular, more popular maybe 10 years ago than it is today, they'll use the UML as blueprint, where they'll go and they'll use a tool like what we were just showing, and they'll create all of these models. And that will essentially be like the blueprint that they'll then hand to software developers and say, here, go implement this. Go convert this into software. And what that allowed them to do is to have some of the more experienced software designers create the design in the UML and then hand it to less experienced programmers, people that are right out of school, for instance, and say, here, go implement just this one class or these methods in this one class. And you don't have to worry about all the context because we've thought about the context. We've thought about how that interacts with the other classes. You just have to worry about that one little class that you're focused on. We'll give you enough detail there that it's a blueprint and you can write that. So that's one way that UML can get used. And then a third way that the UML can be used is as an actual programming language. And you can put so much detail in your models, your UML models, that there are tools out there that you can just click a button and say, generate my code. And so it'll actually produce the software that will run. And so it's as though you're programming in the model and not in the actual programming language. And that's this concept of model-driven architecture. And when you do that, you'll create these what they call platform-independent models and platform-specific models. The idea you might think about there, let's say that you wanted to create a mobile application, something that's going to run on mobile devices. And so one of the examples that we're going to work with that was an assignment was, for instance, think about like a car reservation system or a car rental agency. If they had a mobile app, okay, so you'd have all these concepts in there of things like a vehicle and a location or an inventory of vehicles and drivers and reservations. These would be these concepts that are general concepts, and those would be in the platform independent model. But then the Android version of the app and the iOS version of the app are going to have other classes in them that are specific to how Android works and specific to how iOS works. And those are things that would get added in the platform-specific models. And you would have to have those details in order to produce the actual Android version and the iOS version, because those platforms require different types of classes in them. That's the general idea of model-driven architecture, that you can go so detailed down to, and you can have some common things for the entire system, and then specific things for the different versions of the system that they're going to be running on, like Android and iOS. And then you can just click a button and produce the code for doing it. Okay, so that's the general idea of UML. And then we're going to jump into the different kinds of diagrams. Any comments or questions about that? Has anybody seen UML used in your organization? You see some no's. Any yeses?
They actually, there's kind of a very specific part of the actual entire model of the program where they actually use it as a programming language, and they generate it because it's shared by a whole bunch of teams. And then it's really easy for them to go in and, if we need to add a new attribute, they add it into whatever class it needs to be added. They click a button and it's now incorporated across the entire suite of tools. So they have used that, or they continue to use it, not for everything, but just for a part that's shared and requires frequent change.
Cool. There's a company up in San Francisco Bay Area called Workday. They're human resources, cloud-based human resources company, and they use the UML quite extensively in that anytime you want to customize a human resources solution for a company, so like maybe they're selling to Boeing, for instance, a new hiring package of managing new hires and what their workflow is and how they go through the system. The way that they customize all that, rather than going into a database, for instance, and entering new data, everything is a visual model of the different entities, and it's all UML. And they would go and they would customize it in the UML. They'd create new classes and put values into the different instances of those classes, and they would connect them together in a way. And so that's how they would customize a specific solution for each different major customer. So that's just an example. So the point is that, yes, UML is used in a number of companies in different kinds of ways. And some of them just by software engineers, some of them like Workday by actual people that are very close to sales and customizing solutions for particular customers. Okay, so let's look at a few different diagrams. I like to start with activity diagrams just because I think they're very understandable, they're very straightforward, and they are similar to old flow diagrams that we used to use years and years ago. So a couple of the key concepts here. The solid circle is the start state. A circle with a circle around it is a final state or an end state, and you should only have one start state. And it's possible to have multiple end states, but a lot of times we'll just have one and we'll have everything go into that end state. Okay? And the ovals inside of there, or the ellipses, are the activities themselves. So those are the things that you do. Usually they're little phrases like this, a verb phrase like select wallpaper and so on. So the example here comes from history. It used to be, I lived in Kansas for a long time, and I taught in a small college, and we would have an interterm during January where we just teach one class in between the different semesters. And there's something about January. Every year for several years, I would come home on one of the days, usually that first week of that interterm class, and my wife would have started some home project without having talked to me. There's something about the holidays are done, and I want something new. It's time to change things in the house. And I remember one time in particular, she came down and she had started stripping the wallpaper off of our living room. And I'm like, oh, I don't have time for a project right now. I'm so busy with this class. No. And you know what happens is we hadn't decided on what to put up in place. She just knew she was sick of that wallpaper. This old wallpaper had been there forever. And so how long did we have to wait with no wallpaper on the walls until we picked out, the new whatever we're going to do and put on there? And so this was an example. This is an activity diagram that kind of shows the process of doing that. And what we agreed to, that no work would happen with removing paneling or removing old wallpaper and fixing the walls and any of that until we had selected the wallpaper. That was the first thing. Before we started tearing anything off the walls in the future, that we would select the new wallpaper. And then what you see here is what's called a fork, this horizontal bar. This is a fork, and then the one on the bottom is a join. And so the fork indicates that these things coming out of it can happen in parallel. So on the one side, we could order wallpaper and wait to receive that wallpaper. And on the other side, we could, there's a if then else. So we've got the diamond. So this is a selection and a merge is what we would call this. And so this selection here would say, if there's paneling, we go over this way, we remove paneling. If there's old wallpaper, we remove the old wallpaper. Otherwise, we come down here and they merge together, and then we patch and sand walls and paint sizing, and all of them come together in this join. So we can't go on with putting up the wallpaper until both sides have completed. They don't have to complete at the same time, but we wait here at the join until both sides or all inputs into the join have completed. So that's the idea. It began in an end state, fork and join. We've got activities. We've got selection and merge diamonds in there. So a couple of ways you can check, for instance, whether an activity diagram is correct. Well, in a fork, there can be multiple arrows coming out of the bottom of a fork. Okay? And there should be, in fact, multiple arrows. What's the point of the fork if there's not multiple paths going on simultaneously coming out? And then a join, there can be multiple arrows coming into that join. And again, there probably should be. Otherwise, what's the point? Okay, so that's the basic idea. What does it show? It shows sequential behavior of the system, and you've got the branch and merge. I called it selection, also branch and merge. So if then else kinds of things. Parallel behavior with the fork and the join, and it's similar to what we'll see later, which is a state diagram. But instead of states, we have activities, things that will happen. Okay. When do we use activity diagrams? It's really useful at the beginning of the project, like in requirements, when we're just analyzing a use case. What are the steps in the use case that you're going to do? Okay. When we're understanding workflow and trying to capture that into requirements or just get it documented. Software developers will often use it when they're just trying to understand a complicated algorithm in a function that they're trying to write. It can be useful there. And then it's really useful in describing things that can happen in a multi-threaded application, meaning multi-threads, multiple threads, threads of execution on a processor. So nowadays, we have like multi-core computers, maybe it's an 8-core computer. So that means that you can have 8 things happening simultaneously. And so if you have a single threaded application, meaning everything has to happen sequentially, you're not going to take advantage of those 8 cores. The only advantage would be if you're running multiple applications at the same time. However, if you have a application that is multi-threaded, so it can do multiple things at the same time. So maybe it takes the data that it's processing, if it's got a large amount of data, for instance, and it breaks it up into 8 groups and we'll do some analysis in 8 different threads, and those threads can all run on the different cores simultaneously and then come back together. Now, they don't have to match exactly 8 cores to 8 threads. You could have 100 threads if you want. You have this thing called a scheduler that will put each thread onto a core and let it execute its certain amount of time. Okay. That's the general idea of a multi-threaded application. Any kind of a thing like, on your mobile phone and app, they're all multi-threaded. There's a thread that's dealing with just the user interface and what you see and refreshing that user interface. And then there's background threads that are also executing, that are doing some of the processing. Maybe it's going out to the network and getting some images that it's going to display in the background. And then once it gets the image, it notifies the UI thread, and the UI will then update it with the image that it just retrieved, for instance. And so there's multiple threads running in your mobile application. And so modeling that, saying what can happen in parallel, is a common thing to do with an activity diagram. Okay, so a couple of other things with activity diagrams. We can add these things called states, so we can group a series of activities together into a state. And as these things get really big and complex, those states are great, because then we can hide that. And we can just call this state prepare walls, and we can get rid of what's inside that state and just have the state there with that name. And so you can just abstract and hide some detail. And I believe that's what I did here. Yeah, so here, prepare walls is that state. And so it makes it simpler. I can put more information on one screen. If you want to see what are the details of prepare walls, you double click on that and you'll go see what was on the previous screen. You'll see all of this here. So states are useful. The other thing that's useful is to have swim lanes. Now, I'm not trying to have any kind of gender bias here or whatever. It's just in our family, this is how it worked. My wife is much better at picking out what's going to look good in the house than I am. And so it was her job to select the wallpaper, and it was my job to prepare the walls. And then we had somebody else in the end putting up the wallpaper. But the idea there is that we can have swim lanes. Who's responsible for what? And this is great for people if you're modeling some workflow, or these can be objects in the code. So like one of these might be the UI thread, and the other one might be a networking thread, for instance. And so you can model what's happening on what thread, who's responsible for what parts of the algorithm. So that's a quick overview of what activity diagrams. I think that's the last one I've got. Yeah, on that. Any quick questions on activity diagrams? Okay, I think they're pretty straightforward, and they get used a lot, and they can be used not just in software. You can model your process for your assembly line with activity diagrams if you want to. Okay, the next one I'll look at is, again, a pretty high-level one, use case diagrams. And so this concept of, well, first off, what is a use case? A use case is a set of scenarios tied together by a common user goal. Okay, well, what's a scenario? A scenario is a sequence of steps describing an interaction between a user and a system. So if we go back to our tic-tac-toe game, we might describe one of the use cases as being the make move. I want to be able to make a move or place an X or an O on the tic-tac-toe board. And so the use case, the goal that I have is to make a move. Now there's several different scenarios in which I could make a move. What might one scenario be for making a move on a tic-tac-toe game? Garrett, what do you think? What would one scenario? Have you ever played tic-tac-toe, Garrett?
Yeah, I'm not sure I understand your question.
Okay, so what are the different, so making a move is what I want to be able to do, but what are kind of some of the different situations, might be another word, of the configuration of the board and whether I'm wanting to put an X or an O in a certain place. Those might be different situations. Okay, so one scenario I can say real easy is like this X is here. somebody made a move to place the X in the upper left-hand corner. It was empty to begin with. And so that was the scenario, to place an X in the upper left corner on a space that wasn't taken. That's one scenario. What might another scenario be?
You can place it to win.
Okay.
Right.
Okay. So to place it in
The bottom
will end up being
left.
win. Mm-hmm. Yeah, if it was an O, placing an O in the bottom left, which would be making a winning move. Okay, and that might be a little different, but it's the same goal. You're wanting to make a move. Okay.
So I guess find open spot that might lead to either a stalemate or a win, and then based on, I guess, higher level would be like what the strategy is of how you're going to play.
Right.
So trying to cancel out an opponent's move of creating 3 in a row.
Mm-hmm. Mm-hmm. So maybe making a blocking move. That might be a certain kind of a move that you would make. I'm placing this not to win, but to block the other person from winning. Okay. So it's still a part of that same goal of I want to make a move, but it's a slightly different scenario. Very good. Very good. Another scenario might be trying to place my piece where there already is a piece. So if I'm wanting to put an O up here in the top left corner, I'm trying to make a move. Now, what should happen? It should reject that, but still I'm trying to make a move. It's a special case of making a move, but that's just one of the scenarios. Okay. All right. So those are the concepts. The things that you see here, the oval here is the simple way of representing the use case. The little stick figure here is what we call an actor. Do I have that on the next one? I think I do. Yeah, actors. So the actors are not the most important thing here. What we really want is the collection of all of these ovals. What are the use cases? Because that's what tells us what's the functionality of the system. But the actors are what help us figure out what those use cases are. So the actors are roles that users, or they can be systems that they play. They carry out the use cases. A single user could play several roles. Multiple users could play the same role. And so like here, Alex and Katie, those are two different users. They might play tic-tac-toe against each other. They're both going to fulfill the role of being a game player. Okay, so multiple users are fulfilling that same role there. Okay. I mentioned, we already talked about this pretty well, so I'll skip over it. The idea of scenarios with make move. So here's what we might end up with is something like this. We have a game player that wants to make a move, view the game status, view the game board, start the game. The purpose here is to figure out what are all the things that the system needs to do. Okay. It's just a quick and easy way to do that. There's some special relationships we can have on use case diagrams. So this arrow with kind of a big white arrowhead on it, we're going to see this show up in multiple UML diagram types, and it always means this concept of generalization, where the thing it's pointing at is the more general, and the thing that's being pointed from is the more specific version of that. So make move is the general idea. A specific instance of that that's a little different is when we're making a move but the space is occupied. Okay, and so something different should happen there than what happens generally in the make move. And so different that I broke it out into a separate use case. Okay. That's the concept of generalization. You can see what I said there, an alternate scenario or the same use case with some extra functionality in it. And so that's what that relationship between two use cases is. And again, the point isn't that we got the arrow right. The point is that we came up with this space occupied and we thought about it. It's like, oh yeah, well, what about this situation? Oh, that's a special one. That's really different. And so let's make it separate so we don't forget about it and think about it. We analyze it. Okay. Another relationship here is the includes relationship, which is this dotted line, and it's got with the less than, greater than around it. So here, make move and view game status both use this other use case of checking the game status. Because the idea is we want to check to see, did somebody win, or is it what we call a cat or a tie, meaning that it's full and nobody won, but the board is full. And so that's something that we need to do, and we'll do it from several other use cases. When we make a move, every time we'll check to see what's the game status. Is there a winner? If so, then we'll announce that. Or if the game player, maybe there's some function in the game, in the application, to be able to say, what's the current status? Has anybody won? Then it's going to obviously check the game status. So those are the two relationships in use case diagrams. We've got the use cases, we've got the actors, and we've got these relationships, includes and generalization. Okay. So let's do, I'm going to skip over here real quick. About time for a break, but let's finish up use cases and then we'll take a quick break. So here's a use case diagram that I started using Violet. And I'm going to move this. There we go. And so you can see here I've created two actors. And this is for the homework assignment. I didn't ask you to do a use case diagram, but that's related to that. The idea of creating a car rental software application. So a customer wants to be able to make a reservation for a car rental. And they want to be able to edit that reservation and cancel the reservation. And by the way, these point us to one of the common terms that we use is CRUD. Has anybody heard CRUD? What does CRUD stand for?
Create, read, update, delete.
Exactly. Excellent. Good job, Brad. So that's a common term that we'll use just to remind us when we're thinking about what are all the features that we need to provide. Well, for every element, where do we create it? So like here, a reservation. Can I create that reservation or make a reservation? Where do I update it? And so here, that would be editing it. Where do I delete that thing? Canceling the reservation. It can be real easy to forget one of these when you're dealing with a lot of entities, a lot of data elements, whatever it be. So here it's the reservation. So I want to be able to CRUD a reservation, create it, edit it, or update it, and cancel it. Read is where do I view the reservation? And so maybe that's something that I missed. Maybe I need to add view my reservation. So I'm going to come over here, I'm going to click on use case, and I'm going to click over there and double click on that, and I'm going to say view reservation. Okay, and I'll move that, and I'll draw an interaction between the customer and that new use case. So I can modify my use case diagram. Okay. And here I've got an includes reservation. You can see I've got the, in the tool, I've got the includes and the generalization, and I can add notes and so on. So just jump to the, whoops, didn't mean to do that. I often do that in this tool. I forget to come click on select. There we go. So I have this other actor here, and it's not connected to any of my use cases. And maybe I could draw lines to some of these. Maybe a reservation agent can also view the reservation and edit it because, you know, they need to do those things. But I also want to think about, are there some special use cases that a reservation agent might have that a normal customer might not have? And so here I'm thinking of it. I mean, this could be a person on the phone, or it could be when you actually go to the desk and you're renting a car and they're interacting with the software. What are things that they might need to do that a normal customer might not do? Think of any examples?
Discounts.
Oh, okay, great. Apply a discount. Something like that. It's a great example. What else might they do? Does the customer decide which vehicle they get? Well, it depends. Maybe they do, maybe they don't. But you know, assign a vehicle actually to the reservation. A lot of times that's the reservation agent that says, "Oh, you're going to get the whatever, the blue Chevy Malibu." I just traveled 2 weeks ago to Kansas, and we walked outside and they said, pick one, you know, the whole lot there basically, and said, choose from this aisle or the next aisle. I don't think I'd ever had that experience. They'd always given me keys and said, this is what you're taking. But this time they just said, yeah, keys are in all of them. Just pick whichever one you like. So my advice there is whenever you see those manager specials, I think this was with National or Alamo, they had this manager special when I booked my reservation, and it was cheaper than the regular one. It said that your class of vehicle will be assigned when you arrive. And so there's this fear you're going to be stuck in this tiny little economy car. But for them, that's what they said. Is I got there and said, "Oh yeah, you got the special. So pick whatever you want. You can't have the Camaro convertible over there, but you can have any of these things. There's these SUVs or whatever." So that worked out pretty well for us. We paid less and we got a higher car class. So maybe here, assigned vehicle might be what we're talking about. That usually, and this is where we're going to decide in the system, who gets to do that. Can the customer do that or just the reservation agent? Here I'm saying only the reservation agent can do that. Okay. All right, so that's the idea with use case diagrams. Any questions? Okay, we've been going an hour. I see that it's 5:10. Should we take a 5-minute break real quick? Yeah, some nods. Okay, 5-minute break, 5:15 according to my clock. We'll start back up.
Hey, Kurt, are you there?
I don't think Kurt's joining us today.
He's in the participants list.
Oh, I think that's me because I am logged in as him. Yeah, good question. In order to do the recording, I had to log in as him.
Good, thanks.
Yeah. I know he's around. I just don't think he's joining us today. All right, 5:15. Let's go again. So thanks for being on, guys. I know it's guys and gals. It's cutting into dinner time, and you guys signed up for a whole year of this, and so good job sticking with it and hopefully providing some value, and getting some stuff that's useful for you. Okay, the next thing we're going to talk about is class diagrams, and I've got an example here of a simple class diagram. Simple in terms of we just have the concepts here of we've got a reservation that has particular location, like so this is from the LAX airport is where and there's an inventory of vehicles, and a reservation has a driver. There's some things that are missing as well that we could add as details, but those are the basic concepts. And so we want to talk about these different kinds of associations or lines between them here, the concepts in a UML diagram. So let me move this. So I'm going to bounce back and forth a little bit between my slides and between using our tool there, Violet. So here's a slide. Here's an example of a class diagram as well. The symbols here are kind of old. This is from a tool called Rational Rows. We don't use those symbols much anymore, and I'll show you the example instead. Normally, that lock would be replaced with a minus, and this funky thing would be a pound sign, and everything else would be a plus. And we'll talk about what those mean here in just a second. But the concept here is that we're visually modeling the classes or the entities in our software, and we have these different relationships between them. Okay, and here's another class diagram for the rental car rental agency. This was done by one of the students actually who really got into it last year when I signed the same thing. And so you can see some of the concepts that they have there, vehicles and the different elements in there. Okay. Going back here, you can see there's three sections of a class, this rectangle here. So the top section is the class name. The second section, the middle section here is the list of attributes or data elements or fields. Those are all different terms we would have there, attributes or data elements or fields. And then the third section, the bottom section, is the operations or the functions or the methods. Again, all different names for the same concept, but the operations. So what's the functionality we can do there? This is similar to a simpler technique that we use when we're often coming up with the classes of something called CRC cards. The CRC, they stand for class, responsibility, and collaborators. And the idea is you can just do it on a table with 3x5 cards, and on each card you write down what's a potential class in my system. So maybe a vehicle is a possible class. And then what's that class responsible for? What does it do? Well, it stores the information about one vehicle, like the color of the car, and maybe its identification number, and how many doors, and what its make and model are, and the year that it was made, things like that. Okay, so that's what its responsibilities are. And then who are its collaborators? What does that class work with? So what other classes does it need in order to do its job? And so we see those collaborators through these lines here. We see the class name and its responsibilities through its methods here in the class diagram. Okay, so let's move on a little bit. They show things like classes and interfaces. We'll talk about the concept of an interface in just a second. The attributes and the operations have something called a visibility, which will be listed as either a plus, minus, pound sign, or the tilde. And the visibility, we'll have a slide on that in a second. That means who can use this attribute or this operation? Who can call this method? Which class can do that? In what context can we do that? And the concept of multiplicity as well. Let me back up over here. So here, I have multiplicity on these associations, these lines. That means that one employee can have 0 to, you can't see it very well, 0 ... asterisk, kind of like what we have there, 1 ... asterisk. So 0 or more timesheets. And so this is a class diagram for a system where employees record their time entries on how much they worked in timesheets. And so each employee can have 0 or more timesheets. Here, 1 or more employees can be in a single group, or one group has 1 or more employees. And so a group shouldn't exist if it doesn't have any employees in it, is what that would indicate. So that's what we call the multiplicity there. And then I mentioned the visibility on these things, which we replaced with pluses and minuses and so on. Let's look at visibility real quick. There it is. So plus indicates public, pound sign protected, and minus is private. And some of this you might say, why do I care? You might not need to care too much, but I'll explain it anyway. The idea of public is that anything that can access the class can access this attribute or operation. Whereas private, on the other extreme, only the operations in this class can access this attribute or operation. So if I back up a little bit here, in my example here, the start date and the end date and the time entries, okay, these are all private. They would have a minus on them. So that's saying that the only functions that can change or touch, modify the start date are the functions in this class itself. The add time entry, the submit, the approve, the get time entry. So functions over here, like down in the group or in the get group or in the employee class, they cannot change the start date or the end date. They have to go through functions here in order to change them. Why do we do that? Why do we make things private? It's for protecting that data and the integrity of that data. We can do things like here, we might have an operation that says called set start date. And in that operation, we might put some checks to make sure that the start date is always valid. Like the start date, maybe for a timesheet, we would say start dates are always in the past. We can never have a start date in the future. So we could check that and make sure that the start date is not past today's date. Or a better example would be set end date. The end date should never be before the start date, right? That wouldn't make any sense for a timesheet to end before it's actually started. It should always be after the start date. And so you can put that logic in here to make sure that if somebody is trying to set the start date and passing in a date, that it should always be the same or later than the start date. And so that helps you have some integrity that the data here is not corrupted or bad. Okay? And you can protect that data by making it private. It used to be, before we had object-oriented programming, everything was public. So that meant any code could change any data element. And so like if you had a start date and an end date, there could be functions, in a million lines of code, there could be a function in some obscure file that was changing the start date to some bad value. And it might take you months, hopefully not months, but weeks maybe, to find where is that code that's changing the start date to a bad value and what's causing it to do that. And so this just helps you localize the problems in software and find them much faster and protect that data. So that's part of the concept of visibility. All right. The other thing is associations. We can have uni and bidirectional associations. So that's just what are the directions of these arrows. And so here, this is a unidirectional association, meaning an employee knows about a timesheet, but the timesheet doesn't know about the employee. So you can look at a timesheet and it doesn't know which employee it's on. And that's just the way it's been designed. If there is no arrow on there, then we would say that's bidirectional, which means either we haven't decided which direction it is, or each class knows about the other. Okay. Then we have this idea of generalization. Oops, wrong direction. So here you can see we saw this arrow with the big arrowhead on it, like on the use case diagram. It means the same concept here, that an analyst is a specialized version of an employee. So everything that's true about an employee is also true about an analyst. Same way over here for a project manager. Everything that's true about an employee is also true about a project manager. So an employee has a name and an ID, and so that gets inherited down here in the project manager. Project manager also has a name and an ID because of this relationship here. Same way with analyst, also has a name and an ID. But you don't have to list it there because of that arrow, is what's going on. So that's this concept of inheritance or generalization. All right. And then we'll talk about constraints here in just a little bit. Probably the best thing is, I'm going to skip from here. We get into details of the UML, and I'm guessing you're more interested in just some of the concepts here. For instance, let's look at the driver. So if I open up for the driver class in my car rental application, so the name of the class is driver. What might some of the attributes be of the driver class?
Age.
Age, you bet. What else?
Driving record?
Okay, maybe driving record, or maybe we just need, for instance, driving record. That sounds like a big thing. So that's probably in its own class, and so maybe we have a association with the driving record. What might we need in order to look up someone's driving record?
DMV access.
Yeah, and in order, once we have access, we need their driver's license probably in order to get there. And so maybe we might say license number, their driver's license number, and their state for their driver's license number. And so those would all be good attributes for a class for the driver. And we can keep going. A driver might have a name, they might have a birth date, so we can calculate what their age is. And so that would be a great method there. For instance, get age. So we probably don't want to store their age because their age is constantly changing, right? Every day they get a day older. But as a method, we can calculate the age based on the birth date and based on today's date. And so we can call that method and it will figure out what their age is. And so that's a method. And typically the methods or the operations will put these parentheses on there because sometimes we'll put parameters in those things. Like we might have set state, and we're going to pass in a string is the data type of what we're going to give it. Okay. So for each of these, then, we can specify things like, is this public or protected or private? And probably all of these things can be private is what I'm guessing. So we put a minus on each of them. We might just do that.
What does the tilde do?
Like that?
Mm-hmm.
Right. So that represents what's called package scope. And that's something that's a little odd. So if we would put, let me first explain to you this one, £. Okay. So if I would have another class here, Use that. I'll put down here, and this might be, let's see, what would be a special inherited kind of a driver? What's a special case of a driver? Maybe a commercial driver, somebody who has a license that allows them to drive larger vehicles, you know, trucks and things like that. And so they might be a special kind of a driver. And so I'm going to say that they inherit from, oops, I did that again. There we go. So the commercial driver now inherits from the driver. So the reason why I did that is because now if I have some methods down here, like if I have a method get is valid license, maybe something like that, okay, and that returns a Boolean value, okay, meaning it returns a true or false value. Okay, so it is valid license. I want to ask, is their commercial driver's license still valid? So that's a method, an operation down here in this class. So the question is, what numbers, what fields or attributes can is valid license access? Well, it can access any of them that are defined in commercial driver, and there's none of them. Or it can access any of the protected members from its parent class. And so is valid license can look at birth date and see what its value is, and it can change its value. But it can't change the values for these private members. Okay? Those are restricted only to the driver class. So that's the difference between private and protected. Now, if I made it public, then anybody, any of these classes could then access birth date. That's dangerous. I don't want any of these classes changing their birth date. I want them to go through the set age method that I might create here. So I'm going to make that protected. I'm going to allow this subclass in order to modify that. Okay. So again, to get to your question, there's this one more, which is package scope. And the idea there is that sometimes it's a little too restrictive to say private or protected. I'd like maybe a collection of classes to be able to access a certain attribute, but not everything. And so I can place that collection of classes in what we call a package. And usually that just means they're stored in the same directory or the same folder. And that's what gives them package scope. And so if something is a package scope, then any of those classes in that same directory can access it. So it's just one more visibility level. That's probably more detail than you care about or need to know, but just know that there are these different visibilities there, and they're meant to protect the integrity of the data. Okay. All right, good question, good question. So there's one other concept here that I wanted to talk about, and that's this idea of an interface, okay? And so I can create a interface of, let's say, I'm just going to call it the inventory item. And we can do things like get an ID for the inventory, check it into the inventory, check it out of the inventory, so on. Okay. So this idea of an inventory, you'll notice that it doesn't have that middle section of attributes. It only has methods. And so an interface has a set of methods, and the methods are not actually implemented. It's just like a template for methods that we're going to use. And let me show you how we would use that. So let's say that we're building this system, and we recognize, okay, this is great. We're going to a lot of work to build this car rental agency software. Is there any way that we can make more money on this software? Okay. In particular, we notice renting cars is an awful lot like renting or reserving other kinds of things, like hotel rooms, for instance. Okay. Renting a hotel room is very much like renting a car. You have a reservation, you have an inventory of things, whether those things are vehicles or whether those things are hotel rooms. We have, the inventory might be a lot of cars, or it might be an actual hotel that has rooms in it. You have people who are on the reservation, but, with vehicles, they're called drivers. With hotels, what would we call them? The
Hotel guests.
The hotel guest. There you go, a guest. So what we might do is create those other things. So like here, let's create a guest. Okay, and for vehicle, let's create the parallel there, but that's going to be a room. We're going to rent a room. The guest is going to rent a room. The driver is going to rent a vehicle. But the problem is that starts getting complicated. Our inventory doesn't need to know about vehicles and rooms. It just needs to know about certain kinds of inventory items. So I'm going to change this. Back over here. Delete that. And I'm going to change this inventory now to no longer be an inventory of vehicles, but now it's going to be an inventory of inventory items. Move things around a little bit. And those inventory items can either be a vehicle or a room. And so I'm going to say that implement interface. A vehicle implements that inventory item interface, and a room implements that inventory item. Oops. There we go. So now I have a more general application. So we have an inventory of items. Whether these items are vehicles or rooms, doesn't matter so much. In the same way here, I would change this so the reservation is a reservation of inventory items, not of just vehicles. And I could do the same thing here for drivers and guests. I could create a new interface. Let's go ahead and do it real quick. What would we call that? This is our reserver, okay? Person who's reserving it. Maybe that's not a great name, but we could fix that later. And we're now going to say that the guest will do that and the driver will be that as well. There we go. And again, the reservation is now going to be with a reserver. There we go. We got to do a little cleanup to make it look pretty. That's the idea. Come and delete that one as well. And the reservation is associated with the inventory item now as well. So that's the idea of interfaces and the different entities implementing these interfaces. Get rid of that. Any questions so far? Okay, that's class diagrams.
Oh, is there a tool that's available to kind of generate from code this view so you can kind of get a feel for like what kind of tests you need to support or that kind of a thing?
Yeah, great question. Yeah, there are. There's a variety of different tools out there. They're what we call reverse generation tools that they'll take the code base and you can produce the UML diagram from it. And that's a great way when you've got a big code base, a lot of code, and you're just trying to understand it. What are the things and how are they associated with each other? It's a really good thing to do. There's one of the best ones that I used a number of years ago is called Magic Draw. It's kind of a crazy name, but it was very full-featured, Magic Draw. But there's also inside of the integrated development environments that programmers use, the IDEs, a lot of them will have plugins that will do that. So like Eclipse is a very common IDE used for Java programming, and there's a great UML plugin for that will generate the UML diagrams. Sometimes it's missing some details, but it usually gets you the general idea pretty well. Yeah. Some of the associations, it doesn't always get exactly right, but it usually does pretty well.
Thank you.
Yeah, good question. Okay, so we've talked about use case diagrams. We've talked about class diagrams. The next diagram that I often like to use is a sequence diagram. Sequence diagrams are a way of looking at how the different objects of the classes will interact with each other. And they're great for figuring out whether or not you have all the right methods in here, and whether or not you have all the right lines in your class diagram. Okay, so here's an example. I put a note here saying this is our create reservation use case. So what are the different classes involved in creating a reservation? So I started working on that. So the different elements here, each one of these is what's called an object, and these dotted lines going vertically are the lifeline of that object. And so you can imagine that the life starts at the top and it continues, time goes on down vertically. Okay, so you start at the top and you move down, and that shows the sequence of time. And these long, thin rectangles are what they call activation bars. So that's basically the lifetime of an operation or a method call. And then these are messages, which are basically just method calls. I'm calling an operation, I'm calling a method on another object or an instance of another class over here. So it just shows you the sequence in which things happen. So the reservation manager calls create. It creates a reservation, and then it adds a pickup date to the reservation, adds a drop-off date to the reservation, and then it calls save on itself. Okay? And as a part of saving on itself, it will then send something, which we haven't specified yet, we maybe need to give it a name, to this reservation database object. And it will store the reservation probably in that database. So that's what we know from this sequence diagram so far. So we've got these object lifelines, these activation bars, and method calls. And we can just see the sequence in which things happen. And so I can look at this, and as I am thinking about it, I can think, okay, what do I do next? What do I need to do next? And sometimes I'll realize, oh, I need to do this next, and I don't have the class there. So I might think of a class that I haven't even included in my class diagram. So I'll come back over here and I'll add that class that I need. Or maybe I'll realize, oh yeah, the reservation manager needs to have some association with the reservation DB in order to save itself. Do I have that over here? Reservation manager, yep, there's an association between reservation manager and the reservation database. Okay, so I'm in good shape there. And I can now take each of these methods here, or operations, create, add pickup date, and add drop-off date. Those should go in the reservation class. So I can come over here, and now I know I can put create and add drop-off, add pickup, or what were those dates? I forget. And a really good tool will do that automatically for you. Okay, this is a pretty simple tool. This is kind of an academic tool. And so when I add drop-off date here to the reservation, I had to go and manually also add it over here. Oops, I put those in the wrong class, didn't I? I should have put those. Those are methods in the reservation. I should have put those over in the reservation. Let me fix that so I don't have an error. Apparently cut and paste doesn't work. And add pickup. There we go. Make sure there's no misunderstanding there. Okay, so the reservation has those operations in it. So sequence diagrams are really great for that, just figuring out the order in which things happen and what are missing methods and missing classes that I might have. Here's another sequence diagram for picking up a vehicle, for instance. So here the reservation manager maybe says, I want to get the inventory from the location. Okay, so I get a link to this class. And this dotted arrow means it's returning something. Okay? And I could put a label on there saying what it's returning, but often it's just implied from the name there. And so from that inventory, I'm going to get a vehicle. I'll get one of those back, and then I'll check out that vehicle to indicate that it's actually being taken out of the inventory. And so I'll mark that vehicle as out, and so I send something to the vehicle class and so on. So you can imagine continuing on. What else is involved? It's just a way of thinking through what's the sequence of steps. Okay, so there's the idea of a sequence diagram. I'm going to skip ahead just a little bit here. We talked about visibility already, and yeah, I'm going to skip those for now. There we go. Here's another sequence diagram, same kind of a concept. You'll see that I even sometimes put actors on my sequence diagrams because maybe there's a user interface involved, and I can think of a person, clicking a button or something that starts a flow of activity. And so I like to do that at times. So there's a sequence diagram. All right, couple more, and then we'll see what kind of cleanup we need to do at the end, what time's left. So this next one is a collaboration diagram. This is very straightforward. This is the same thing as a sequence diagram, just in a different format. It just looks differently, but it's conveying exactly the same information. And so tools will often go back and forth between sequence and collaboration diagram. So here, if you go back and look at this, the first thing is you ask the user interface to get a timesheet. And then you ask the timesheet server to get a timesheet, and you pass in a string. Number one is the employee asks the user interface to get a timesheet. Number two is the user interface asks the timesheet server to get a timesheet, and it passes a string in so it knows which timesheet it's looking for, and so on. Number three is over here, and 4 and 5, and so on. So you can follow the flow of things, but you're focused more on the collaboration. What classes collaborate, and in what ways do they collaborate? Sometimes this is a less complicated view than this is. So it's just different ways of looking at the same thing. But the UML defines both of them as dynamic diagrams showing the sequence of things. Okay, so that's collaboration diagrams. Pretty straightforward. State diagrams. I'll bet some of you have seen state diagrams before. They've been around a long, long time, since like the 1960s, maybe even older than that. They're used in a lot of different fields, and they're a part of the UML as well. They just kind of adopted them and said, yeah, we'll just add a slightly different UML flavor on them. So they've got the same beginning and end, or initial and final states like we had on activity diagrams. And they look like activity diagrams, but they're a little different. Instead of these being activities, these are states. The activities or actions are usually the arrows that are going between states. So it causes you to go to a different state. So here we have a timesheet. The timesheet can be empty. It can be assigned. And while it's in the assigned state, you can add time entries and remove time entries. And so under this bar inside the state, these are actions that you can do that keep you in the same state. They don't cause you to leave and go to a different state. You can delete the timesheet, and it moves you over here to a deleted state, and you can continue to remove time entries from there. And once you've got this bracket here, which is a condition that says basically if all time entries are removed, then we're now in the final state. And then over here, you can go to submit and approve, and you have these different states. Okay. Here's an example of an entire system. Like this is basically a thermostat. You can just model a thermostat with these simple states. Either the heater and the air conditioner are both off, so you're in an idle state, or the air conditioner's on, or the heater's on. But you would never want the situation where both the air conditioner and the heater are both on, right? That'd be a bad thing, right? You're using a lot of energy and combating each other. I remember in Kansas, we had this big wood-burning stove, and it was probably too big for the size of house that we had. And I remember one winter day, it was cold outside and snowing, And, so I loaded up the wood stove and had it going, and all of a sudden we heard something. What is that? The air conditioner kicked on. Okay, the furnace, the wood burning stove was producing so much heat that it triggered the AC to come on. That was a bad thing, but they weren't both controlled in the same system. But this is a great way of modeling an entire system. These are the operations that cause you to go, so if you go above a certain temperature, then the air conditioner turns on. Then when you're at the desired temperature, it turns back off. When you go below a certain temperature, the heater comes on. When you get at the certain temperature, it goes back off. So it's an example of a state diagram. You can also add, I don't have it here. You can have substates. So you can put, like back here, you could put several of these things inside of a larger state, and it just creates like an abstraction around them and simplifies the number of arrows that you have to have. Like if everything in here, I wanted to put these 4 states into one active super state, for instance, and then just have one arrow going to final, meaning that you can go from any of those states to final. You could do that with okay, the last one, next to last, two more here. I think I showed this the other day, a deployment view. This is one of my favorite first diagrams to look at that shows the big picture of the system. What are the different hardware elements, and then what are the software components? The software component is a bunch of software that all goes together and accomplishes something. Like here, a database is an entire component, or a time tracking server that does the logic about storing things in the database, GUI, and so on. So that's a deployment diagram. And then a package diagram. These look like files or folders is the idea. And so this is how we might group the software into these different packages. And we can have packages that contain other packages. It's pretty straightforward. Okay, so those are basically the different kinds of UML diagrams. I'll mention one last thing on UML, and that is this thing called OCL, Object Constraint Language. Object Constraint Language. So you can add to any of these diagrams these constraints. It's basically mathematical statements about the diagram. And it adds in just a lot of the logic. If you're wanting, it's especially used when you're using UML as a programming language. If you're wanting to generate code from your diagram, you've got to put a lot of detail into your diagram. And this is the way you often do that, is with these things called object constraints in this OCL. So here, for instance, I'm going to specify this method, OCL in state. It's got a parameter, it has a return type, and you can then associate that with elements of your diagrams. Okay, so like here, remove element is a method that's specified on this. Looks like this is a state diagram. So either it's in the empty or the not empty state, and when you remove element, it can come back here. And so here, the precondition is that the OCL is in state, so it's not empty. Okay, so it should have been in that state. And then the postcondition is the size at the precondition equals 1 implies that OCL in state was empty. So this is a logic statement saying, when should OCL state empty be true? Is essentially what's happening. And we're just defining the pre and post conditions for how remove element works. All right, so don't worry about all the details there. The point is you can put these mathematical concepts onto UML diagrams in order to make it very precise and specific. Personally, I've never worked on a project where we went that far. Okay, I know people who have, but you have to really be committed to doing it in that way in order to spend the time to do that. Okay, so that's it on UML. Let me pause for a second. Let's see, how are we doing on time? We're just about out of time. We've got 6 minutes left. I've got some other things on patterns, but what questions? Any questions on the UML? Any things that are fuzzy still? Any questions about why? Who cares? I'll maybe say a little something about context or popularity now. The UML is, in software organizations, a little bit falling out of favor. There's not really anything replacing it. People just aren't doing as much design as they used to, I think, is what is happening. It tends to be used in an informal fashion a little more frequently than in a formal fashion. I think that's just because there's so much agile development that's going on where they're not doing big designs. They're doing small designs. And so they don't create big models and documents like we used to. So it's still useful to know, but you don't see big UML models in a lot of organizations. There's still some organizations that use it a lot, use it extensively, and it's very much a part of their DNA and part of how they do design.
One question I had is, we talked about a little bit last time with the requirements and just specifying the environment. And I noticed that's often something that kind of gets forgotten about in the design, is what environments need to be supported. And you had a little bit there with the deployment diagram,
Right.
but is there any way to incorporate, like, you know, when we were talking about, like, you know, I think it was the like activity view, or even like the use case diagram, like, is there a way to show, or a standard way to show, like, in these contexts, in this environment, this is what we're supporting? Like, this actor is acting on these stages almost, or?
Right, yeah. It depends on what level you're doing things. It's like at a use case diagram, I won't go all the way back there, but yeah, I've definitely seen things in use case diagrams. People will do stuff that's not standard UML all the time. Okay, they'll use the stuff and they'll draw extra states and boxes, and I've seen that where in a use case diagram, they'll put extra boxes around some of the use cases and say, these things are going to happen in this part of the system, and these things are going to happen in this part of the system, and this actor is a part of this system, and this actor is a part of another system, where they'll put like states around them. It's not standard UML, but it conveys some information that's useful to them. And in my book, whatever is useful to you is fine, unless you're specifically using a tool and trying to generate code from it. The whole point is to communicate important information. So yeah, I definitely see it on use case diagrams. I don't know if I can think of other examples other than deployment. Deployment diagrams are the place where you're supposed to communicate that information. What's a part of what system? And yeah, good question. So on Wednesday, I'm going to talk a little bit about TDD, test-driven development, and we'll talk about testing and how we do software testing a little bit. And TDD is about testing, but it's largely about design. And the UML is more often used for high-level design, getting the big pieces together, like here in this deployment diagram. What are the major pieces of our software? But then the little details, you can imagine having a class diagram like this that's very detailed, very low level, and having, a big system might have hundreds or even thousands of classes in it. And a lot of places are not going to create UML diagrams for 1,000 classes. All of those do. It's just a lot of stuff. And so when do you make those decisions of what should be a class? What should the methods be in there? That's where TDD, I think, is a useful tool for designing what should be a class, what should the methods be in there, and figuring it out as you're writing your code. And so I'll walk you through what TDD is and how that works, and a little bit of code examples on Wednesday. I'll pick up I'll pick up with the design patterns. Let me just show you briefly a little teaser. We've got 2 minutes. So here's one of the design patterns, the facade pattern. Okay? What do we usually think of as a facade? Think of it, for instance, with buildings. What's a facade on a building? Something like a fake front, right? Have you ever seen, I know like in I grew up in Kansas, and we've got all these old towns, old downtowns, old buildings, brick fronts, whatever. And they would go and they'd put new fronts on them to make them look modern and new. And then 30 years later, they'd take those old ugly facades off, and you'd see the old building, and they'd restore it because it was classic and cool architecture or whatever. But that fake front is what they would call a facade. We'll do that in software. When you have software like this, let's say we've got some system here. It's got a bunch of classes in it, and there's all these other classes that are using this component or library or whatever. And so they know about all the details in there. There are some problems with that. One of the problems is it's hard to change what's inside this package because a lot of your other client code is going to break because it's dependent on all these details down in here. So a common solution is to use the facade pattern, in which you introduce this new facade class that hides all of the details of the underlying system, and all of the other software that wants to use this package or set of software has to go through the facade, a common interface. And there's certain advantages and disadvantages to doing that. An advantage is now you can make all the changes you want down here behind the facade, and your clients don't need to know about it. So you can improve code here, you can make modifications, you can fix defects, and it's not directly seen, doesn't require changes in your client code here. Okay? So that's just a quick introduction of a concept that's called a design pattern, the facade design pattern. We'll talk about a couple more of them on Wednesday, and then we'll get into the TDD stuff.
When you had the reservation manager in the car rental, is that an example of a facade?
Not quite. What we're doing there is we're creating what I would call a framework, actually, in which you can have multiple instances of that framework. The vehicle reservation framework, the hotel reservation framework. Maybe you could do a flight reservation. They're all using the same framework. Yeah. That's a good question, though, but that's what I would call a framework. Okay, well, there were some good questions today. Thanks for bearing with me. It's 6:02 on my clock. If you've got questions or things that are still muddy, post them in the minute survey. If you haven't created a UML diagram, I encourage you to go take a stab at it. Let me just mention, if you go and get the Violet software, you'll Google it and you'll download some Java code. And in order to run that Violet software, if you're running it locally, it's not real clear. You will type something like this, java-jar, and then whatever that Violet UML editor jar file is. It's not really clear in their documentation. That's how you'll start it. And that's how I'm running this software here. If you want to use Violet, the example that I just showed. And if you have any questions on that, if you're trying to use it, shoot me an email if it doesn't work for you, and I'll help you try and figure out what's going on. Should work because it's Java. You will need Java installed on your machine, but most people's machines have Java on them, unless you're running a Chromebook or something like that. Okay. Thanks for your attention, and we'll see you on Wednesday.
Thank you.
Thanks.
See ya.
Yep.